Hello and welcome back. This is Wednesday's lecture for week 13. I hope you had a fantastic Easter. We're going to be talking about the first part of chapter 26. So chapter 26.1 and 26.2. I recommend that you read those sections. So the first part of the chapter just deals with mirrors. So the first mirror I'd like to talk about is a flat mirror. Imagine that the image is represented by this blue arrow where the top of the image is at the top of the arrowhead. And the rule that we're going to be using, well, with one exception, for our ray tracing is that we're going to start all of our rays from the top of the image. So all of the light that appears to be scattered from the top of this image, that's what we're going to use as the to figure out where the top of, sorry, let me try that again. We're going to take light scattering from the top of the object to determine where the top of that image is. So I'll draw the image in red and the object in blue. For example, for a flat mirror, we have two rules for ray tracing, and they're pretty simple. One is that we take a parallel ray coming in and striking the mirror. And then we remember that the angle of reflection is equal to the angle of incidence. And here the angle of incidence and the angle of reflection are both 0 with respect to the normal. So it means it's going to come right back out the way it came in. And my second line, this is the second ray tracing rule. If this black line represents the principal axis, which is kind of the center of the mirror, if you will, where the ground where you're standing is the principal axis. So the bottom of the image is where the principal axis is. I take this point of intersection from the top of the image to where the mirror intersects the principal axis, and then I just use what you already know. The angle of incidence equals the angle of reflection, and so if I try to make this incoming angle equal to the outgoing angle, it looks like I have a line somewhat like that. Great. Well, you can see that the rays don't converge out here. There's no image that's formed on this side of the mirror. And so we say that there is no real image formed. It's not real because the location where the image actually is, you know this because you've done the experiment a million times, is actually here on the other side of the mirror, and there's no light that can get to that side of the mirror. So here I've listed my pro tips for doing ray diagrams. I actually found these confusing at first, and now I find them to be simple, but I think it's because I have these rules in my head. For one thing is, you should use graph paper, right? Don't use unlined graph paper like I'm doing now. And we're going to make this small simplification model that all of our rays make small angles with the principal axis, which means that we can model all of our mirrors, not just a plane mirror, as this straight up and down line on your graph paper. Now I'm going to be using curved lines just to sort of to help visualize what's happening, but if you want a high degree of accuracy, I recommend using this simplification model where you just do your graph paper and all of your surfaces, whether spherical or flat, are going to be modeled as a flat line, so the y-axis on your graph paper. And also use arrowheads. Here I was trying to be careful to use lines coming in and arrows coming out. That's because if no rays actually converge out here, then what our eye does, what our mind does to form an image, is it extrapolates. It figures out where the light appears to have been coming from. So it's, I probably know that your image is basically just an optical illusion. You don't actually have a friend behind the mirror. Well, let me just use green again. Okay, changed my mind. Okay, so I'm going to follow this rule. I'm going to follow the arrowhead back since there are no rays converge on this side of the mirror to see where they appear to be coming from. So following the second ray backwards looks like something like that. And following this ray backwards looks like it would be something like that. Well, the two rays converge here, so that means I can say the top of my image is where those points intersect. Now, probably you recognize that since this angle has to be equal to this is the angle of incidence, has to be equal to the angle of reflection. Then this angle is equal to this angle. And this height where the top ray strikes the mirror is the image height. And this height is the God, I keep getting that backwards. Is the object height, and this is the image height. Okay, because these triangles are similar, these angles are the same, these are both right triangles, that means that all of the interior angles have to be the same, which means the triangles are similar. And also, since this height is the same for both of these triangles, right, for this triangle and this triangle, that means they are identical. So these are identical triangles, which means the object height is equal to the image height, and it also means that the image distance, which is the distance from the mirror to the image, is the same as the object distance. So the image distance equals, and I'm going to put a minus sign here because we know the image, since it's virtual, has to have a negative sign. I don't know if I discussed this last time, but a rule of thumb for determining what sign of all of our quantities have to have is to see if light actually travels there. If no light goes to the location of the image, then our image distance is going to be a negative number. And our object distance is positive. Real light comes from our object, so they have opposite signs. That's why the image distance is equal to the negative of the object distance, because the image distance is negative. And also, just using similar triangle arguments, you notice that the height of the object, the ratio of the height of the object to the distance of the object is equal to the ratio of the height of the object to the distance of the image. So I'll just write that down in as a ratio. I have to use negative sign again because the image distance is negative. So we're actually going to use this relationship quite a bit, that the object height and the image height are related by the ratio of the distances. One last thing I'd like to define is magnification, capital M. That's just the ratio of the image height to the object height. Well, here it is. Here's the ratio of the image height to the object height. So I can just write that this is equal to the magnification. So a couple things to notice about magnification. If this ratio is greater than 1, the image is enlarged. So if M is greater than 1, our image is enlarged. If this ratio is less than 1, that means that the image is bigger than, if it's less than 1, it means the image is bigger than the object. Oh my god, I got this totally backwards. Epic fail. This ratio is right, but for me to, I should have just left it like this. It's 1 over M. Okay, let's do the image height over the object height, and the image distance over the object distance. Now it's equal to M, and M is the ratio of the image height to the object height, HI over HO. So if the image height is greater than the object height, then M is greater than 1, and if the object is bigger than the image, then the magnification is less than 1. So even though we use magnification normally to mean enlarged, if magnification doesn't necessarily have to mean that it's bigger. It only means it's bigger if the magnification is bigger than 1. The other thing to notice is if we end up getting a negative sign for magnification, that means that the image height is below the principal axis. For image heights and objects heights above the principal axis, they have positive signs, and they have negative signs when they're below the principal axis. I'm just talking about image height. So if magnification is negative, that means our image is inverted. So here I can classify the image as real or virtual. Well, no light actually goes there, so it's a virtual image. And then I have to decide, is it inverted or upright? And it's upright because they're both above the principal axis. And finally, is it bigger or smaller? And it's the same size. Okay, that's pretty much all there is for planar mirrors. You have a couple of examples in your homework where you're asked to find the distance of the image given how far away you are from the mirror. Okay, so for a concave mirror, imagine that you are decorating the Christmas tree and an ornament falls off and your glass bulb breaks, and you look inside the glass bulb and you're like, oh, look at that little picture of me. And then you get closer and closer to this reflecting surface, and you'll notice the image will start blurring, and then all of a sudden you're like, oh my god, what is this huge nose, right? Your image will turn from a tiny upside down picture of yourself when you're out here someplace relative to the radius of curvature to if you put your nose inside the center of curvature. In fact, if you put it even closer inside the focal point, your image gets really big and upright and actually virtual. And maybe you've had this experience with a makeup mirror already, so maybe you're familiar with this concave mirror. Some people find it helpful to remember that a concave, as opposed to a convex mirror, has the word cave in it. So imagine that you're in a cave here, you're kind of enclosed. So this helps some people remember that concave means you're looking at this surface instead of the outside surface, which would be convex. Alright, so let's draw our image. Remember I said if you're doing this on graph paper, which I recommend, and we're using small angle approximation, all of your lines are going to intersect a straight line here on the principal axis. But we're not going to do that. I think it's easier for me to demonstrate the reflection and incidence relationships using the curved surface. But again, just for maximum accuracy on your graph paper, remember you're going to be using a straight surface here. Alright, so here are my ray tracing rules. I do parallel in, focal point out, and number 3 says focal point in, parallel out. You know you only need 2 lines to find the point of intersection, so you could do ray tracing images all day with just 1 and 3. And I hesitate to use 2 sometimes because 2 with this, unless I make the small angle approximation, really gives me pretty terrible results. But with your graph paper, using the straight line, use number 2. Use number 2 because it's great to have a third line that verifies your image location is correct. So we'll use this third point as a check. Alright, so drawing my first line, parallel in, focal point out, starting from the top of the image. Remember I mentioned that there's one exception to starting at the top of the image, and that's if you're inside the focal point of your mirror. Maybe I didn't mention that, but I'd like to mention that now. Okay, so parallel in. Now, which way would this ray be reflected? Let's think about this. Any line that goes through the center of a sphere is going to be perpendicular to the surface of the sphere. The same is true for in 2 dimensions. A radius line is always perpendicular to the surface. Is always tangent to this to the line of the circle. So here's a radius line going from the center of stands for center of curvature. So from the center of my circle, I know that this line is perpendicular to the surface. So if I do my angle of incidence equals angle of reflection, that means my reflected line would have to look something like that. I broke my rule. I should say always use arrowheads. Okay, so we can tell that just visually that the array coming from infinitely far away, or one that's parallel to the axis, is not going to go through the center of curvature of the of the mirror. That's kind of counterintuitive. It's actually going to go through a point that's halfway between the center of curvature and the surface of the mirror. And this point is called the focal point. And that's the definition of focal point is where where paraxial rays will converge. Did I write that anywhere? No, I guess I will now. So a ray that comes from infinitely far away will be parallel to the axis, and any paraxial ray will converge there. And furthermore, you can tell just looking at this geometry and using some triangular arguments that the focal point for a spherical lens is half the radius of curvature. So this is worth putting a box around. I'm going to use this. Now we have to decide what sign should we use for the focal point. For the focal point for a concave lens is going to be positive because light actually goes through that focal point. And next we'll be looking at a convex surface where the light doesn't actually travel to the focal point, and so that will have a negative focal point. But in both cases, they're equal to half of the center of curvature. Okay, now let's try another line. The third one is focal point in parallel out, so let me try that. So starting from the top of my object again, going through the focal point of the lens, I know that it is going to come out parallel to the axis. Great. So I have two rays that are converging here, so it appears that my image is right here. But just to check, let's do real quick, let's go straight through the center of curvature, and I know that a line that goes through the center of curvature is going to have to come back out through the center of curvature. So if it comes in like this, it needs to come out like that. So that's just a useful check to make sure that I have my image location in the right place. I just use this third line straight through the center of curvature to make sure the image is right. So let's classify this image. You notice that the image is below the the principal axis, which means it's inverted. It's smaller than the object. Means our magnification is less than 1. And real light travels to this location, so the image is real. So real, inverted, and smaller. Your textbook does a good job, I think, of deriving the relationship between the image distance and the object distance and the focal point, and we just use this similar triangular arguments. Remember that tangent is opposite over adjacent. So the tangent of this angle alpha is equal to h over the difference between the object distance and the center of curvature. And then, since we know that opposite angles are equal, this angle alpha is equal to this angle alpha. And looking at this smaller triangle, we notice that the tangent of this angle is equal to the image height divided by the difference between the center of curvature and the image distance. So you can set those two angles equal to each other and do a little algebra, and you'll come up with this relationship for the relationship between the image and object distances and the center of curvature. Now, they use slightly different symbols than other textbooks, and I find it to be confusing to keep track of what is P and Q. So let me just write it in terms of the object distance and the image distance. It's 1 over the object distance plus 1 over the image distance. And instead of using the center of curvature, I'm going to use the focal length, because that's a more general form of the equation that will be useful to us when we look at lenses, for example. And just remembering that f is equal to c over 2, you can solve all of your mirror equations with this. Really, the only pitfall is getting the signs wrong for the focal length and the image distance. Before we move on to convex lenses, I'd like to show you that there are other possibilities for this. This is actually a rather complicated arrangement. We already talked about what happens with your makeup mirror. You know that the image behaves differently depending on whether you're inside or outside of the center of curvature or the focal point. So just really quickly, I'd like to show you what those differences are, and you have one homework assignment on that. And I'm just going to draw two rays for each of these. So first one, parallel in, focal point out. Next one, focal point in. Oops, sorry, focal point in. Parallel out. So that's the one we just did, where the image is inverted, smaller, and real. And now if I'm inside of the center of curvature but outside of the focal length, do parallel in, focal point out. My second line, parallel in, focal point in, parallel out. Now it's still real, it's still inverted, but the image is bigger than the object. And then lastly, let's look what happens when we're inside the focal length of the lens. My first line is parallel in, focal point out. Now we're focal point in, parallel out. Okay, we seem to have a problem here, right? We said at the beginning that all of our rays begin at the top of the image. Well, we're going to have difficulty getting to the focal point. If I were to draw a line from the top of the image to the focal point, it would go out here to outer space and it would never interact with our mirror at all. If I were to trace that backwards, I would know that the converse is true, that any light that's being scattered off of the top of our image that has gone through the focal point has to come out parallel to the axis. So this seems like an exception to the rule where we said all of our rays begin at the top of the image. Okay. Well, we see that no rays actually converge out here. So if the rays don't converge, remember the pro tip number 3, I think it was, was if the rays don't converge, follow the arrows backwards to see where they appear to be diverging from. Alright, so let's give that a try. I'll draw these in yellow. I follow this backwards, which means it's going like this. Follow this one backwards. Starting this arrowhead, I see that backwards has to be in this direction. And so our image is upright. It's virtual because no actual light goes there. And it's bigger. Alright, so your homework does take you through this situation where you notice that the image changes from being inverted to upright and from smaller to bigger, and it asks you what kind of mirror it is, so I think that you'll know how to answer that question. Alright, finally let's look at convex mirror. So now we're going to be on this side, so the outside of the Christmas tree ornament before you've broken it. And let's see what happens to the rays now. This is still going to be this center, and halfway between the center of curvature and the reflecting surface is going to be the focal point. So following my rules for ray tracing, first one is parallel to the axis, parallel in, focal point out. Okay, well, the focal point's here, so does it make sense for light to travel through the surface of the sphere to that focal point? Well, no, it doesn't make sense, right? What does make sense is for it to appear to be coming from that focal point. So I'm going to draw it like this just to show you what's going to happen okay, sure, I'll just draw it like that. When I'm doing my ray tracing diagrams, I follow the rules. I go parallel in, focal point out, which means I know no actual light goes there, but those are my ray tracing rules. Focal point out, okay, and I'm doing it, even though no actual light goes there. And then my next one says focal point in, parallel out. Well, I'm going to go right to the focal point. It says to, even though I know no actual light goes there. And parallel out. Focal point in, parallel out. So my ray is going to be, oh shoot. Okay, this is why I kept the spherical surface, because I think it's useful to see. If I were to draw a line from the center of curvature, you can see that the angle of incidence is equal to the angle of reflection. Maybe you can't see that. Here's my normal line. Right, so this angle is equal to this angle, and here my normal line it's like this, so this angle is equal to this angle again. So I've been faithful to the angle of incidence equals the angle of reflection. So you can kind of see that this makes sense just from a reflection point of view. But from a ray tracing point of view, all we have to do is follow the rules. Parallel in, focal point out, this would be the first arrow that you would draw, and focal point in, parallel out, this would be the second arrow that you draw. And then we look at the pro tip. We say there's no rays that actually converge here. So I follow these arrows backwards. See, this is where people can get confused. So it's very important, I think, to follow this rule. Follow this arrow backwards to see where the rays of light appear to be converging from. And maybe I'll use red here to say, okay, I follow this backwards. That means this one's doing that. And following this backwards, this one's doing that. And so my image intersects, it's not upside down, here, which means it's upright, it's virtual, no actual light goes there, and it's smaller. Let's do one last check using the center of curvature. I know that if it comes in through the center of curvature, it's going to go straight back out through the center of curvature. And so that's a useful check to make sure that our image is in the right place. Right. Again, if you're doing this on graph paper, you're going to model your reflective surface as a plane, so this would just be one straight line. and you'll notice you'll get a high degree of accuracy. Your fix, all 3 points will be at the same place, and your image distance and magnification will be correctly predicted. Your textbook has a very useful table, this table 26.1, which shows the sign conventions for mirrors. And I would say that you should memorize this. I mentioned that the only way to make mistakes with our mirror equations is to get the signs of our image and object distances incorrect, and same with the focal length. We can get the sign of the focal length incorrect. So this is the cure for that, is to memorize this table. Or you can just use the rule of thumb, which I mentioned before, which is if no light actually goes there, then you can think of that, then that image, then that quantity has a negative sign. For example, the object location, well, real light scatters off it, so it has a positive, sign. Object is behind the mirror. Well, that's only if you're Alice in Wonderland, or you're actually your reflection is the object for another. So it's a compound reflection. For everything that we're going to be doing, the object distance is going to be positive. And same with the image location. If it's behind the mirror where no actual light goes, it's going to be negative. It's positive when real light goes there. In other words, in front of the mirror. And whether the image is upright or inverted says what side of the principal axis is it. So this is just like our normal graph paper where y is positive above the x-axis. And the focal length is going to be negative if it's in a place where light doesn't go. For example, this is going to have a negative focal length because light doesn't actually converge at that point. Let's do a couple of examples from your textbook. The first one is this dental mirror. And what I like about this problem is it doesn't tell you what type of mirror it is. It doesn't say whether it's a concave or a convex mirror. We just have to figure it out from the givens. So we know that the image distance is 1 centimeter. Oh, sorry, that's the object distance. A tooth is 1 centimeter. And the image is 8 centimeters behind the mirror. Well, if the image is behind the mirror, then no light is getting behind the mirror. So I've got to remember to use a negative sign for that. So di is minus 8. So now when I plug this into my mirror equation, 1 over the object distance plus 1 over the image distance is equal to 1 over my focal length. But let's see if we can figure out what the focal length is. If I solve this, this is 8 over 8 minus 1 over 8, that's 7 over 8, and if I flip that upside down, that gives me 8 over 7. We're asked to find the radius of curvature. We know that f is equal to c over 2. So that means I can multiply this by 2, and I get c equals 16 over 7, which is 2.29 centimeters. To determine the magnification, I need the image height over the object height. That's the definition of magnification. Well, I don't have the image height, but I do have the image distance, so I can remember this relationship, that hi over ho is equal to minus di over do. Di is minus 8, so minus 8 is plus 8. The object distance is 1, so that gives me a plus 8 for magnification. Here we're given what kind of mirror it is, and we're even given the radius of curvature. So if I know that it's concave, that means the light will actually converge to that point. So the sign for the focal length will be positive. And I know that the focal length is half of my center of curvature, so I can just write this right away. F equals 2.1 meters with a plus sign because it's equal to c over 2. And to determine the image distance, I'm going to use the mirror equation again. My object distance is 7.9 meters. And we are asked to calculate the image distance. So let's plug that in. 1 over 7.9 plus 1 over the image distance, which we don't know yet, is equal to 1 over f, and f has a positive sign. Now if I solve this for di, your 1 over x key is very useful here. I would enter this on my calculator as 2.1 1 over x minus 7.9 1 over x equals. And then don't forget to invert it at the end, and you should get 2.9 meters. Now to determine the magnification, we don't have the image height, but we have the image distance and the object distance, so you can take minus di over do and you'll get minus 3.62. You can see that because minus 2.86 divided by 7.9 is about a third. Is the image real or virtual? That's a concave. There's a physics intuition way to do this and a mathematical way to do this. The mathematical way to do this is to look at the sign of di. We know that the image distance is 2.9 meters. Positive image distance means light actually goes there. That means it's a real image. The other way, using your physics intuition, you know it's a concave mirror. And we're standing outside of the center of curvature, so that corresponds to this picture. We're outside the center of curvature. Our image is real, it's inverted, and it's smaller. I believe that answers that. If you have any questions or concerns, please don't hesitate to text or email me. Okay, be well. Good luck.